There's a machine in California that has to be kept colder than deep space. Not because it is dangerous, but because if the outside world touches it even slightly, the quantum state inside begins to collapse. And that is what makes this story, Music, so disturbing. Quantum artificial intelligence is not just showing us faster computation. It is forcing us to face an old question that physics has never fully answered. What does reality do before it is observed? Inside a quantum computer, particles can exist in multiple possibilities at music once. But the moment information leaks into the environment, those possibilities, music, disappear into one definite outcome. Now, machines like Google's Willow are turning music, that mystery, into technology. And the deeper we look, the more it seems that the solid world music around us may only be the surface of something far stranger underneath. At the center of a quantum computer is not a giant engine, but a tiny chip filled with qubits. And unlike normal music computer bits that are either 0 or 1, qubits can exist in a superposition of both possibilities at the same time. That strange ability is what gives quantum computers their power. Because when many music qubits become entangled, they can process an enormous space of possibilities that classical computers cannot realistically follow. But there is a problem. Superposition is music, incredibly fragile. A small vibration, a stray photon, or a tiny electromagnetic disturbance can, music, destroy the quantum state, which is why these machines must be cooled to temperatures colder than the space between galaxies. For a brief moment, the machine creates a protected zone where music, the universe, is almost prevented from interfering. And in that silence, the qubits can do music, something that still feels almost impossible. They can calculate while reality has not yet chosen music a single answer. This mystery began long before quantum computers, with the double-slit experiment, one of the simplest experiments in physics and also one of music, the most unsettling. When particles are sent through two slits, without anyone measuring which path they take, they create an interference pattern, as if each particle somehow traveled through both slits at once. But when a detector is placed to discover which slit the particle used, the music interference disappears, and the particle behaves as though it chose only one path. That is the terrifying detail. The difference is not just movement or collision, but information. When the universe has no record of the path, the particle behaves like music, a wave of possibilities. When the path becomes known, those possibilities, music, collapse into one result. This is the measurement problem. And after nearly a century, physics can predict what happens with incredible precision. But it still cannot fully explain why one definite reality emerges from many possible ones. Einstein believed particles, music, should have definite properties before we measure them, because the idea that reality only becomes definite, music, through observation felt incomplete and almost unacceptable. He thought there had to be hidden information underneath quantum mechanics, some deeper layer explaining what particles were really doing before we looked. But John Bell turned that philosophical argument into a test. If particles carried hidden instructions, their behavior would have to obey certain mathematical limits. But quantum mechanics, music, predicted that entangled particles would break those limits. And when experiments, music, were finally performed, the universe sided with quantum mechanics. Again and again, entangled particles showed correlations too strong to fit Einstein's classical picture. Meaning reality at the deepest level is not built the way common sense tells us it should be. That is why this is not just about music, strange particles in a lab. It means the solid, familiar world we experience may emerge from rules that are not solid or familiar at all. Google's Willow processor, music, brought this ancient mystery into the age of quantum artificial intelligence because it showed that these delicate music quantum states are no longer just laboratory curiosities, but something engineers can control at a serious scale. With 105 qubits, improved coherence, and major progress in quantum error correction, Willow demonstrated that quantum systems can become music more stable as they grow, which is one of the key steps toward useful quantum computing. But the most shocking part was its benchmark, music performance, completing in minutes a calculation that would take an unimaginable amount of time for a classical supercomputer. This does not prove parallel universes, and it does not solve the measurement problem. but it makes the question impossible music to ignore. If a quantum computer is truly using superposition and entanglement to music, explore a massive space of possibilities, then what is actually happening inside the machine while it calculates? The uncomfortable truth is that we know the mathematics works, the machine works, music and the predictions work, but the meaning underneath remains unresolved. And that may be the most terrifying thing quantum artificial intelligence, music, has exposed. We are beginning to build the future on top of a reality we can use with incredible precision, but still do not fully understand. The strangest part of this story is that quantum behavior is not something trapped inside laboratories or hidden only inside machines like Willow, because the same rules are operating right now inside the atoms of your body, the music, air around you, and even the light moving through the room. Your hands feel solid because they are constantly interacting with everything around them. Photons, air molecules, heat, surfaces, vibrations, and all those interactions force the quantum possibilities to become the stable, music, classical world you experience. In other words, the reason you do not see your hand in a strange superposition is not because quantum physics disappears at larger scales, but because the environment is always measuring it, always recording information, always pulling the system into one ordinary-looking outcome. This process is called decoherence, and it helps explain music, why the world feels definite even though its foundation is quantum. A quantum computer does the opposite.